Now it's in the repo. So yeah, congratulations, you are dedicated. You came to class when there was water falling from the sky. Good job. Oops, I guess we need to be in full screen mode. Okay. Raise your hands if you think California is ridiculous and this is just normal weather. Yeah, I kind of suspected there was going to be a high proportion of people who made it here who have lived in places with actual weather. Okay, makes me nostalgic. I haven't, yeah. My PhD was in Manchester, England, and this is like a normal Monday. So I'm finally remembering to kind of put together a reading list for topics. I think that a lot of you will benefit from these different books. Just a reminder, we have 3 different books that are all free that I kind of think, depending upon what you're interested in, you should probably check out the topics. So Bishop is a classic book. It's what this class has been taught off in the past when Dessau does it. Bishop is very much a Bayesian book, and the way that Bishop approaches ideas like even regression can be taken from a Bayesian point of view. So if you want to understand how even things that you don't think of as Bayesian are Bayesian, I would suggest taking a look at Bishop. I don't know why this fell out of play mode. Okay. The Hastie and Tibshirani book, that book is a classic in statistics. Like if you take this class at a graduate school level, it will probably use the Hastie Elements of Statistical Learning book. Okay? Both of those books are free and in the public domain. The new book, Bonaccorso, I guess is how you say that. I'm not real good with Italian. The Bonaccorso book is, again, it's something which is on the O'Reilly website. And if you're on UCSD VPN, you can use those O'Reilly books for free. So that doesn't really have numbered chapters because it's an online book. Clustering Fundamentals covers what we're talking about this week. Okay, and the Bonaccorso book, I just wanted to reiterate, it's a lot more programming implementation oriented. It does have math. It does appear to me on my look through it that the math is pretty good. Very summary, like these are the results. Not a lot of this is how you derive it. If you want derivations, go to the Hastie book. Okay, so K-means, that's where we're at. So the idea of K-means is simple, so simple it's almost dumb. I have a bunch of data points. I have a model in my head. This model is these data points are actually generated by K separate distributions, okay? Like, if I was measuring height in this classroom, you would assume that there are 2 distributions, one for males and one for females. And when I draw a student and I just measure your height, I don't know, for whatever reason, I guess I'm blindfolded or something, I don't know whether you're coming from the female distribution or the male distribution. My job is I've got a bunch of height measurements and I just want to assign people to the mean that they came from, right? So in that world where I have blind measurements and I need to figure out or infer what mean generated them, if I have in my head a model that this came from 2 means, this data set, or it came from 4 means or 6 means, my job is simply to assign data points with x's to clusters with Cs. Now, moving cluster, like the idea of a cluster, like I don't know a priori where the cluster is. I don't know where the mean is for males or the mean for females. I just want to fit my clusters to the data I see in the class. Okay? So here's the basic idea of K-means. Pick two cluster centers, probably at random, and then look and see, okay, here's a bunch of data points that are all closer to this mean, and here's a bunch of data points that are all closer to this other random mean. Well, now that I've assigned those, all I need to do is go ahead and recalculate the mean given the empirical assignment. I assigned these 23 people to the mean number A. Right? I assigned 14 people to this other mean B. Now I calculate the empirical means and I shift my estimate. And I do that again and again and again and again. Okay? Once I have the means, I find out, again, who's closer in the data points. And I end up reassigning people that used to belong to mean A now belong to mean B, right? Because every time we do this update set, we are going to end up shifting where the means are and shifting which data points get assigned to which mean. This is a repeated, iterative process. And you keep doing it until the means aren't shifting as we go from iteration to iteration. Okay, so K-means as a clustering algorithm is relatively dumb. It's relatively iterative, but it's simple. Like, you can code this yourself in not very many lines of code, and hint, you're going to have to on an assignment. At least doing it the dumb way is easy. Doing it a computationally efficient way is a little bit harder, and when you use scikit-learn to do this, you're taking advantage of, all those computer programmers, making it possible for you to do this not with 20 variables, but with 200 variables, okay? Because if you try to do this the dumb way with 200 variables, it's literally going to take forever. Okay, so that algorithm, that fairly simple algorithm, it has implications. Like always, I want you to take away from the 118 series this main thing. Every algorithm is designed for a particular kind of problem, right? And if you try to apply an algorithm to a problem that mismatches the design of the algorithm, you're in for potential problems. You're in for getting an answer that is going to lead you astray. So what are the assumptions behind this kind of an algorithm? Fundamental to K-means is the idea that the clusters themselves are convex. Now, I didn't have the time to make a slide, so you're going to get my artwork. Okay, on the chalkboard. Go front and center, right? So I'm going to draw some data points that are non-convex. All right. So this is elongated and wiggly, right? If you ask me where is the mean, I'm just gonna frickin' guesstimate that it's maybe somewhere around here. Okay? So what if I have more data points and I have another mean, right? And maybe this is lodged inside a cluster that is convex and maybe significantly more compact. So here's what's going to happen during K-means, right? when I recalculate the mean, so like, you know, at some point these means are moving towards this position, right? If this is like the final actual mean of the cluster, when it's over here, then I'm going to end up in the situation where like maybe these data points over here actually are closer to this mean, right? So this mean is going to start to shift out of this dense little cluster. And as this mean shifts into place, maybe eventually these guys flip back over to here, or maybe they stay with that cluster. And you end up, as you can see very quickly, like if you've got elongated directions, like it's easy to get these data points belonging and being closer to this cluster. Really easy. And the way K-means works is purely based on distance, right? Whichever one of these means this data point is closer to, that's where it belongs to. And when it belongs to that, it shifts the mean with it. Okay. So K-means is meant for convex clusters of equal variance, right? Just imagine the case where we have one variance mean like this and one that's got variance like yo, okay? It's the same situation. It's just not got an anisotropic nature to it, okay? So I covered the idea of how K-means works and the Voronoi tessellations in the pre-lecture. So if you're looking at this graph and you have no idea what this graph is, I highly encourage you to go back and watch that pre-lecture. I'm not going to cover that here. Okay, so you can see, oh, I forgot, I did actually steal from scikit-learn's docs. I didn't have to do all that drawing, right? These are examples of when you have unequal variance or you have, you know, anisotropic distributions or something non-convex. Or what if you have 3 actual generating processes, but you put in only 2 means on K-means, right? What if you pick the wrong K value? Hey, 118A people, what happens when we pick the wrong hyperparameters on our models? And how do we pick the right hyperparameters? Anybody got a suggestion for us? Yeah? Yeah, so you can use some kind of model selection technique, like, for instance, grid search, to pick the right hyperparameter. So this class, I'm not going to spend a lot of time talking about how to do model selection, but I am, when we get to the notebook at the end of class, going to show you one way to do model selection. Okay? All right, we already said this, right? Initialize the means. Pick random ones. Assign data to clusters given the means you picked. I want you to note the words I'm using to describe this. Assign data to clusters given the means. Where have we last seen the word given? Probabilities like Bayesian style, likelihood functions, probability of the data given the parameters. Oh, it's a likelihood function, isn't it? Okay. And then we need to update the means given the data and the clustering. Oh, wait, given 2 things, given a joint probability on the right-hand side, we're going to do an arg max, right? Update the means. Find the means that maximize the posterior probability. So yeah, I just want you, K-means as we're talking about it right now, we can just write algorithmically like this. but I want you to realize it's part of a bigger framework that we're going to talk about through the course of this week and next week called expectation maximization. It's a two-step process that involves, well, likelihood functions. Okay, so here is a data set, which is exactly the kind of data set that K-means is meant to solve. It's 3 generating processes. I'm setting up 3 means. I already know the right number of means, and I'm telling K-means I want 3 means. These processes have overlap. So, there's places where green dots are, kind of invading the territory of the red dots. So it's not an easy or perfectly separable, but there's definitely places in the data density which basically are green's territory, right? And so when you watch K-means in operation, you can see we start with a random location. In this case, the algorithm literally just picks 3 random data points and makes those the means at the start. And then we play the game. If another data point is close to this proposed center, then it belongs to that center, and we recalculate where the center is on the next step. Okay? And you can see we slowly converge to a place where we are accurately representing the centers of these means. Okay, some things that are true here. We've accurately represented the centers of these clusters. Is orange in the same place as orange on the original data? No. This is not categorization. We haven't said these are all the cats over here and these are all the dogs over there. We've only said these data points are more similar to each other than they are to those other data points. We haven't put labels on them. Now, once you make a clustering, you can, as a human being, come in and say, all right, this is all the cat images, okay? Right? You can label it after the fact. But the algorithm is not doing that. That would be a categorization task, which is the topic of 118A, not 118B. Okay, now what happens when we have, is my animation not working? There it goes. Okay, what happens if we have the same data, but we throw in too many means? Well, the final answer we get doesn't have any bearing to the underlying process, right? No surprise. Okay. I'm also saying that because there are other clustering algorithms that don't work this way. That will give you a hint when you're trying to model them with the wrong number of means. Okay. So how could we know how good a clustering is? There are generically 2 ways, 2 ideas, I shouldn't say ways, 2 broad categories of approach. If you do have labels, you have a ton of metrics available to you. If you do know, in a supervised learning sort of way, this data point is a cat image and this data point is a dog image, you can compare your clusters to those labels. There are a bunch of techniques. I'm not going to cover them, at least in this lecture. Maybe I'll go into it a little bit later. Things like the RAND index or mutual information metrics that can tell you, hey, how well is your clustering capturing the labels that you have for your data points? Now, it may sound weird that if I have labeled data, why am I bothering with an unsupervised algorithm? Okay? This can still be a reasonable approach. Maybe you don't have labels on all your data points, but like 1 in 100 data points you've got a label for, okay? So you can use those labeled data points to check your clusters and see if they're any good. So that's a pretty common reason why you might not do just a plain old straight categorization task in a supervised way. But let's just assume, let's take the far more interesting and more difficult problem, which is we don't have any ground truth label. The only thing we've got to assess how good is our clustering is the data itself. If I have a bunch of data points that live inside a cluster, are they actually more similar to each other than to a data point that lives in a different cluster? That is the only math available to us to evaluate the goodness of our final clustering. So the main way people do that, and there are a couple of other indices that you can apply, but the one that people usually use, or you would call the thing they learn the first in classes like this, is called the silhouette score. Now, the silhouette score is exactly what I just described, right? The mean distance between a sample and everything inside your cluster minus the mean distance to data points outside your cluster, divided by a normalization, right? This is a score between +1, good, -1, bad, right? If a given data point, like you can do the coefficient as an average, right? You can take the average across all your data points and just say, for my clustering, this is the silhouette score. It gives me an idea of how good the clustering is. Or you can choose to calculate the score for each data point individually. And that silhouette score tells you something about where your data point lies. If that score for that data point is close to 1, you're living lovely right in the nest of your cluster, right? Almost everything close to you is elements of your cluster. If the score is 0 for this data point, you're probably right at the border of your cluster and a different cluster. And if the value is negative, you're probably assigned to the wrong cluster. Okay? So when you look at it as an average over an entire clustering, then if the average is high, then you've probably got dense, well-separated clusters, right? The ideal case for clustering, where the means are like this, well-separated. Okay? If it's like whatever, 0.2 as the average, then probably your clusters are highly overlapping in space. Okay, so this is what, when you do a silhouette, what it looks like, okay? So here are some generating data. As you can see, it looks like the generating data actually has maybe 4 different generating processes. 1, 2, 3, 4. We're trying with 2 means right now, okay? So this green set of dots over here, this is the silhouette plot for all the individual data points. Some of the data points that live right in the center of the cluster have very high silhouette score. Some of the ones that are at the edge of the cluster, like out here, are going to have lower silhouette scores. Okay? Here's the black cluster, sorted. Here is the average across all the data points, across the whole clustering. Okay? So now you can see why they're called silhouette scores, right? If we order, for every data point, we order it from highest silhouette score to lowest silhouette score, we've got a silhouette. Very inventive, right? Great naming. Okay, so if we want to compare different clusterings, by the way, I just frickin' copy-pasted this from the scikit docs, okay? I didn't do anything amazing here. So you should definitely look at this link, right? But if we want to compare different clusterings, k equal to 2, k equal to 3, k equal to 4, we can keep calculating silhouette scores. So here's 2 clusters, and here's what happens when we have 4 clusters, which is the right number of clusters. right? This matches the generating process. So you can see visually that this looks good on the clustering. You can see that the silhouette score is higher than the last time around, right? And you can see that all the clusters have similar silhouettes. That's kind of one of the big tells that this is a good clustering. If all the clusters have really similar silhouettes. Here, you have very different silhouettes, very different numbers of data points in each cluster. We know for a fact that K-means does not do well with unequal cluster sizes, and yet here the silhouettes are radically different, okay, with way more data points in the black cluster. Here, the clusters are much more similar. It's what K-means really is looking for. Okay, what happens when we go to like too many clusters? Well, some of the things that we think of as human eyeballs as one cluster get broken apart into multiple clusters, and they make tiny little clusters that have very weird silhouette shapes. Okay? So this is called silhouette analysis, because people literally look at the shapes and they diagnose whether this is a good match for the data. It's not as simple as just saying, oh, pick the highest average silhouette value, okay? It's not that simple. The way this actually works when you're doing a statistical analysis is you diagnose what you're seeing in the silhouettes, okay? Are the clusters unequal? Are the shapes roughly the same? These things tell you whether the clustering is any good. But you can, indeed, to an extent, just look at that average silhouette score and at least see when stuff is very bad, right? 6 clusters is clearly not as good as 4 clusters, which we know to be the ideal. But note that the average on 2 clusters is actually higher. It's just that the shapes were bad. And you have this unequal number of data points, which tells you K-means is not working right. Okay, so this is, if you've got no labels, this is how you do model selection, right? When you're doing clustering. Use silhouette analysis or something else like the Davies-Bouldin index or whatever no, I forget. No, Davies-Bouldin, you have to know the labels. There's another one that has 2 people's names that I'm getting mixed up on, but whatever, right? You can go look in the scikit-learn metrics docs, and you can see that there are other possibilities. Yeah. Is there a systematic way to?
Like bake in domain knowledge into like silhouette analysis or any type of clustering analysis?
The answer is almost certainly yes, but at this moment, I'm not able to come up with an example. Do you have a particular application you're thinking of?
I mean, I've worked with like genomic data,
Uh-huh.
and there we use like Louvet clustering, and then aside from that, it was just I guess, what made biological sense, and that was kind of defined by the research, like prior research.
Right. So, like, I've seen all kinds of unsupervised things in biology where people are like, look at this Tisney or whatever, right? And generically, they're validated by saying, like, oh, people think of these 2 cell types as being very similar, and look, they're close together, right? So that's one way in which expert knowledge can come in, is that you can have, rather like the subset of labeled data, right? You can have some labeled data that you use to validate a clustering for sure. Is that kind of the thing you're thinking of? Okay. Okay, let's do an example with more interesting data. We've already seen the MNIST back in the beginning of class, right? It's pretty hard as a categorization task. I shouldn't say pretty hard. It's definitely solvable, but it requires a little bit more than minimal effort to solve, right? It's more than a toy problem. So one of the ways in which you can see that clustering is not the same thing as categorization is if you try to K-means MNIST. So first thing you're going to find if you try to put in this 784-dimensional vector into K-means on scikit-learn is you're going to find, like my computer did when I did it, that it starts eating all of your RAM, and then your Mac OS falls over and you have to reboot. Okay? Why did it do that? Well, it's not inherently the 784-dimensional stuff. It's that those 784 dimensions are non-normalized, right? They're numbers between 0 and 255. And it just so happens that when you try to deal with that, sometimes the K-means in high-dimensional space, if it's not normalized, weird stuff can happen. Like some of those pixels, like the corners, are mostly empty. They have very low variance. They're almost always going to be white, okay? Some of those pixels are varied. There's pen strokes in them. Sometimes there's not. Sometimes there's different heaviness on the pen stroke. So the ones that are high value that tend to be close to 255, those ones rule. They just take over. Those variables rule the metric space. Okay, the ones that are low variance, you know, they have relatively little influence. And sometimes the math, as K-means is trying to settle on keeping a mean in one place, ends up in these weird circles, okay, where it doesn't ever settle down. And that's when it eats up all your memory. But if instead, if you normalize this high-dimensional space, you at least have a chance, right? I'm saying this in part to call out that last week I put out a notebook called Vector Normalization that I didn't cover in class. And I really, really, really want you to go look at that notebook if you haven't, okay? Okay, so if you normalize these vectors so that the low variance pixels have as much contribution to the representation as the high variance pixels, you have a chance of doing K-means, but you still got to have a lot of memory and also be using a clever implementation. So maybe the right way forward is to reduce the dimensionality. Take it from 784 dimensions down to 2. Right? Remember we talked about PCA in the beginning of class as an idea at least. We'll get into the details of it later in the quarter. But we transform it into a lower dimensional representation. In this case, just 2 dimensions, so we can plot it because, you know, that makes it a toy problem that we can actually understand a bit. But note that in the course of the PCA, what we're doing is like, yeah, you can see that the zeros live over here, right? It's pretty obvious we should be able to cluster the zeros, but what the heck is even going on in the middle over here? It doesn't necessarily look like a convex cluster is really going to do the job, okay? But we're going to try anyway. So this is what happens when you use 2-dimensional PCA on the MNIST data set and then try to cluster the first 2 principal components. There are 10 digits, right? 0 through 9. So I put in 10 means. Do those 10 means correspond with any digit even clearly? No, right? Like if this red is the zeros over here, right? It got broken up into 2 clusters. By the way, this graph here on the left-hand side, you may note it's not as dense as the right-hand side. The right-hand side is 70,000 images. It's full MNIST data set. The left-hand side has subsampled it down to 5,000 random images out of that 70,000, just so that I could actually see Voronoi tessellations. Otherwise, I was blotting them out with the dots. And in the course of that subsampling, you can see what is not apparent over here on the right-hand side. This area in the principal component space is much more sparsely populated than this region over here. Again, we know K-means wants to have equal-sized clusters. And we know it wants convex clusters, and it seems like we're busting, right? Even where we have something that might be a single really great convex cluster, it gets broken up by K-means into two separate clusters. So, right, the idea is this. If you have a categorization data set, a categorization problem, do categorization, right? Clustering is not the same thing as categorization. It is using the data itself to find patterns that might be of interest to you. Okay, I'm going to skip this in the interest of time. So I want to say one of the things you can do with K-means, and it's an interesting thing where if you look at my pre-lecture, I couch it as other people were interested in the idea of vector quantization, and the algorithm they came up with turns out to be basically K-means, just from a different viewpoint. Okay, that also means you can use K-means as a vector quantizer. I can't even say words, right? If you can take a RGB image, red, green, blue, each color gets a byte. That means you got to use 3 bytes to represent every pixel. Okay? Well, those 3 bytes, the 3 colors, red, green, blue, you can consider them as a vector, a 3-dimensional vector, RGB. What we can do is we can say, well, instead of having, in this case, a 3-byte RGB actually enables 16 million colors. And empirically, of those 16 million colors, 96,000 are in this image, right? We can quantize those 96,000 images down to 64 unique colors. We use K-means clustering to find these prototypes, these centers of lots of very similar colors, like all these greens that are in the pagoda. Like, they're unique. Every pixel, that green is not quite the same as the pixel next to it. But we can cluster all those greens together and replace them with one prototype, one mean of pagoda green. And then just replace all the pagoda green with that one pagoda green. And that's what we're doing in the quantized image on the right, which if you look at it on a good screen, not up here, you can see differences. It's obvious it's not the same image, but if you never saw the image on the left, it wouldn't bother you. It wouldn't look like a bad image, okay? And because we're quantizing the 3 bytes down to only 6 bits, that's what 64 is, it's 2 to the 6. So we can get less than 1/3 as much memory and still produce pretty much the same image. And that's what image compression algorithms do. That's what a JPEG does, right? It compresses the image, gets rid of repetitive information. Okay, so that's K-means, things we can do with it. Let's go over, I did put this notebook into the repo, and I want to show you how K-means works when we do it in scikit. Okay? It's not hard, but I want to make sure some of you maybe haven't already had 118 or you're not familiar with scikit-learn. I want to introduce you to the ideas behind scikit. So scikit-learn is set up in different settings, different sets of the API, right? So if we go to the API, you'll see these are the broad categories, okay? Clustering lives here in scikit-learn cluster, But some other things that we might need are things like metrics, ways to measure, like silhouette down here. Okay, so when we use scikit-learn, we need to import what we need. So from scikit-learn clustering, we're going to get K-means. From scikit-learn metrics, we're going to get the silhouette score. Okay? So scikit also gives us ways to make data, like my 3 Gaussians. So make blobs here. I'm not going to go into it. But here's how all scikit-learn estimators work. An estimator is something like K-means, or a linear regression, or a neural network. They're all estimators. See, scikit is class-based, okay? And every class, everything in scikit-learn is a class. K-means is a class. Cross-validator is a class. The metric is a class. And all the ones that are models or machine learning algorithms, they all inherit the estimator class. The estimator class is the base class of all of them. An estimator implements 3 basic functions for you: setting parameters, training the model, predicting new data. Okay? That's it. Okay? So how do you set parameters? You set parameters at the moment you instantiate your class, right? This is the class constructor. I say K-means, give me 3 means. I set the parameter, K equal to 3. Okay? At that point, I now have an instance of K-means class sitting and waiting for me. Okay. If your estimator is something that's supervised machine learning, then it's going to be fit the model and predict the model. If it's something like K-means, which is unsupervised learning, it's going to be fit the model and then transform. Okay? No, sorry, I said that wrong. It's not unsupervised, supervised. The distinction is whether it's, sorry, it's not, it's something which has actually a prediction component or something which is a pre-processing element, right? Like taking means, z-scoring the data, right? That's a transform. Something which can produce predictions, my bad, is in fact got to predict, even if it's unsupervised. My apologies for saying that wrong. Okay, so, all right, so you can fit and you can predict a K-means. So you can do those in one go, or you can do it separately, right? I could do it like this. I could do K3 fit the points, and then I could do K3 predict the points and get my cluster labels. I can do it in 2 steps, or I can do it all in one go, which is where I had it in the notebook. And again, you can get this notebook and go look at it, okay? So once you have a set of cluster labels, right, what it's saying is it's just giving you, this data point here belongs to cluster 1, and this data point here belongs to cluster 2. The very first thing I encourage you to do is to make sure that your means are equal size. Just histogram those output labels, okay? And you'll see that in the case of applying 3 clusters to these 3 really nice actual generating processes, you're going to get the output labels are roughly equal numbers of data points. Yay! Okay, what happens if I make a set of data points that are grossly wrong for K-means, right? Green has got so much variance compared to orange. Well, when you do a fit predict on the same 3 K-means, it's pretty clear you've got a problem, right? And you would also see this if you did that silhouette graph, which again is in scikit-learn docs, right? You can go take a look and even get the code for that silhouette graph. So if I click on metric silhouette score, I get all the stuff. And you will find at the bottom examples of using silhouette score. And this is where I stole those entire set of slides from. And if you scroll to the bottom, you'll see code for generating those silhouette graphs. That might be useful for you. Okay? Copy, paste, repeat. Okay. So again, you can use the average silhouette score as a kind of very crude model selection. But again, be aware that without looking at the full silhouette analysis, you're potentially missing out, right? It's not as simple as maximize the silhouette score to find the right number of clusters. Okay. I did a lot of blah blah today, and I want to apologize for that. I do want this class to be a little bit more interactive, but I have to be brutally honest, like getting prepped for this lecture was kind of last minute because of a variety of other things. So I want to preview where we're going with this. So on Wednesday, we're going to go with mixture of Gaussians, which is a more Bayesian kind of approach. We're going to get back into doing this, and you're going to see how mixture of Gaussians is a Bayesian version of this. Same thing, okay? We're going to get into full EM, and I want to, like, if we can, I'd like to make these kinds of notebooks more in-class exercise, where you've got to fill in part of it, and we can discuss, like, on a data set that we can actually cluster, right? How we know whether it's any good or not live, okay? So we're going to try to get to that. Which also means that what I want to do is really make sure that people are coming in here with that pre-lecture under their belt, okay? So let me just encourage you that way. That's all I had. Does anybody have any questions? Because nobody interrupted me a single time today. Well, that's not true. I have one interruption. Okay, then we're done with the 2 minutes early. Run away while you still can. Hopefully it's not raining. Have fun, everybody.